Today I want to talk about the mole concept, one of the two most important concepts that we'll discuss in chemistry this year. And the basis of this mole concept is so that we go to the lab and we take a mass and it makes sense. So if you look at your periodic table, let's take a look at carbon as an example. So on your periodic table, you'll see the following information for carbon. Atomic number 6, symbol is a capital C, and then there's a number at the bottom of the box, 12.011. This is called the atomic mass, and it's the average atomic mass of all the carbon that one would encounter in the universe. The mass is 12.011 AMUs, where an AMU is an atomic mass unit. Now, we've talked about conversion factors quite a bit in this class, so let me give you a new one. And this is one that I want you to commit to memory, and it is one we will use quite a bit. 1 AMU is equal to 1.6605 times 10 to the minus 24 grams. So the mass of a carbon atom would be 12.011 times the quantity of the mass of an AMU in grams. What I would like to do now is to set up what the mole actually is and why it makes sense for us to use it in chemistry. So I'm going to start with a simple problem. We have one carbon atom. And we know from our AMU definition that one carbon atom is 12.011 atomic mass units. Carbon atoms cancels. Notice this is dimensional analysis like we've been doing. Now I have a new conversion factor. I know that 1 AMU is equal to 1.6605 times 10 to the minus 24 grams. And now, atomic mass units cancel. Now there exists a second conversion factor, and we call this conversion factor the mole. So 1 mole is equal to the mathematical reciprocal of 1.6605 times 10 to the minus 24. That's 6.022 times 10 to the 23rd. This is a new conversion factor that you need to know. So my last conversion factor is 1 mole is 6.02 times 10 to the 23rd. Because these last two numbers in the numerator, here and here, are mathematical reciprocals, when I multiply them together, I'll get 1. So the numbers themselves cancel. So this leaves me with carbon having a mass of 12.011 grams per mole. And although I couldn't ask you to measure the mass of a carbon atom in the lab, I certainly could ask you to measure the mass of a mole of carbon atoms, because that's just going to be 12 grams. Something that we definitely can do in the real world. Notice that a mole of carbon is the same as its mass in AMUs, which gives me another conversion factor. 1 mole is equal to the gram formula weight. So let's say we wanted to compute the molar mass of sodium chloride, NaCl. Consulting the periodic table, we find that sodium has a mass of 22.99. And chlorine has a mass of 35.453. We're going to add those together. When we add those together, we'll get 58.443 grams per mole. That is our molar mass, also known as a molecular weight. Also known as a gram formula weight. So let's apply this and let's look at the molar mass of calcium oxalate, which is the primary component of kidney stones. Calcium oxalate. I have 1 calcium, and according to the periodic table, that is 40.078. I have a carbon atom that's 12.011, and I have 2 of those, so I need to multiply that by 2. And I have an oxygen atom, 15.9994, and I have 4 of those, so I need to multiply that by 4. And again, I think if we use the Chemtrix app, should download this over the weekend. It's free. Chemtrix tells us that we have 128.097 grams per mole, which, by the way, gives us another conversion factor. The gram formula weight of a molecule in grams is equal to 1 mole. We've also learned that a mole is an Avogadro's number. Now this is abbreviated as capital N and a subscript capital A. That's 6.022 times 10 to the 23rd. Today we've also learned that 1 AMU is 1.6605 times 10 to the minus 24 grams. So 3 new conversion factors today. All right, so for H2SO4, I have 2 hydrogens, each is 1.0079. So that's 2.0158. I have 1 sulfur, which is 32.01. I have 4 oxygens, which is going to be 64. I add all this together, I get 98.03 grams per mole. .06 grams per mole would work. 98.1 grams per mole would work. 98 grams per mole would work. It simply depends on how much I round before I add up all of the masses.